So we went ahead and found this solution. We had been working for a very long time to solve this Legendre equation for unknown value n. And we arrived at this right here. And I said that we were going to kind of discuss what this means. So I'm going to select it all painstakingly. Probably didn't get everything. Yeah, I lost some of it. Oops. Oh, God. What am I doing? I wish there was like a select button that didn't make me draw around the whole thing like a box. A box would be good. I bet there. Okay, we're just going to do it in two parts. So we're talking about the solution we found. There's our C1. So we're going to ask ourselves sort of, what does this mean? There's our solution right there. And it's a lot to look at, but just remember, given some n, we would be able to sort of like plug in that value n, and then this is just a bunch of numbers. It's still infinite series, but it is a bunch of numbers. So for example, it's going to depend on something special, and let's just work through some examples to think that through. So if n equals 4, we're going to have y equals C0 times 1 minus 4 times 4 plus 1 is 5. So 4 times 5 over 2 x squared plus 7 times 5 times 4 times 2 over 4 factorial x to the 4th plus minus 9 times 7, sort of going down until we reach, see, 4 minus 4 would give us 0 over 6 factorial x to the 6th. And then if you imagine any term after it, you know, you had n plus 3, n plus 1 reappear, n plus 3, n plus 1. So if you hit n minus 4 right there, you're going to hit n minus 4 again. So it's actually just going to be plus 0, plus 0, plus 0 right there. Your C1 is going to give you x minus 6 times 5 over 3 factorial x cubed plus 8 times 6 times 3 times 1 over 5 factorial x to the 5th minus 10 down through 4 minus 5 is minus 1 over 7 factorial x to the 7th. And we skip over the 4 minus 4 here because you're always subtracting odd numbers on the C1 terms. So this one will continue, but this one stops after the x to the 4th term. So sort of if we call these two things y1 and y2, what we're going to find is that y1 is just going to be equal to 1 minus 4 times 5 over 2x squared plus 7 times 5 times 4 times 2 over 4 factorial x to the 4th. And then y2 still is an infinite series. But that y1 does end. And it's going to be sort of the reverse story for, if you think about n equals 3, you're going to have that y1 is still an infinite series, but y2 will stop, and it's actually going to get caught up after just the second term right here. When you get to here, you're going to have n minus 3. So 3 minus 3, that becomes 0. Everything after it is 0. So y2 is just x minus 5 times 4 over 3 factorial x cubed. It's been truncated. So what it depends is on if n is even or odd. If n is even, what's going to happen is you're going to have this C0's solution, y1 will sort of stop. And we saw here it stopped at the same power as your n, went up to x to the 4. And then if n is odd, like we had when n equals 3, then y1 is fine, but y2 only has up to power. Here it went up to x to the 3, and so again, it's going to be up to x to the n. And so that's worth noting. Sort of you're going to have these lead us to the Legendre polynomials I promised we would be talking about today. Let's see if I can get a straight line. It's pretty good. So observing this, leads us to the Legendre polynomials. And those polynomials are just going to be these special truncated examples that we get for even and odd n in our solution. And the rule for that is going to be given by sort of two parts. If you set c sub 0 equal to minus 1 to the n over 2, and then 1 times 3 down towards your n minus 1 over 2 times 4 down through n, for n equal to 4, 6, dot, 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 and c0 equals 1 for n equals 0, a special case. And then for your evens, if you set c1 equal to minus 1 to the n minus 1 over 2, and then there you'll go 1, 3 down through n is your odd number, but then on the bottom you'll do 2, 4 down through n minus 1 is going to give you your even number. We do that for our odds, n equals 3, 5, 7, dot, 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 with c1 equal 1 for n equals 1. Then the solutions we get out of this, c0 times y1 and c1 times y2. Again, only thinking about for even or odd values of n respectively. Those solutions, and just to be clear, when I say C0, Y1, I'm talking about here's our Y1 that we got for an even number. Here's our Y2 that we get for an odd number. So we think about Y1 for even numbers, Y2 for odd numbers. Those give us the Legendre polynomials. And then what we're going to do is we're going to denote these as sort of piece. Oh, wow. Why did I move so far over just now? P sub n of x, because they're functions of x. And then P0, P2, P4, so on and so forth, come from the even part of the solution that gets cut off, and P1, P3, P5, so on and so forth, come from the odd part of the solution that gets cut off. And we'll write what those are in the next set of videos. These special coefficients, you don't have to commit to memory. I'm going to give you the polynomials that come out of those special coefficients. Don't worry. The real part you need to focus on is we're defining P0, P1, P2, P3, P4, P5 based on what happens when we solve this differential equation, get this fancy solution, and then plug in different values n that lead to either y1 or y2 being a polynomial that cuts off at some point. And I'll show you what those specific polynomials look like in the next video.